November 30th, 2015. It's been a little while. I'm in this Barron's EZ Chemistry. This page is 232, factors related to the magnitude of K. This is related to chemical equilibrium. Now, going over the main ideas, the main philosophy of this has been quite difficult because there are a lot of main ideas in there, a lot of things that scientists have missed over many years of, chasing red herrings and getting all their models wrong. But just so people can understand, the basics of stellar evolution are involving chemicals, and for the most part, what drives chemical reactions is the chemicals want to achieve the lowest amount of heat. Also, the entropy increases. So as the heat goes down, the entropy goes up, meaning the heat and the temperature goes down, the enthalpy, and then the entropy goes up, the disorder goes up. And we see this with stellar evolution itself. The star starts out as a very simple construct with all the free radicals and plasma, and it's really hot. And sure, there's a lot of entropy, which is disorder, but eventually it cools. The enthalpy cools down, and more disorder takes place because the chemicals start combining with each other, making molecules. And if you further that, if you go many billions of years into the future, as the heat, the enthalpy, the heat decreases, the entropy will go up with the formation of life. As far as I'm concerned, life itself is very highly random, very disorganized, which then in turn gives rise to organization, which is really weird. But I just want to go ahead and read this out. Some reactions are said to go to completion because the equilibrium condition is achieved when practically all the reactants have been converted to products. That has a large part of it with cell evolution. You have the free radicals, the ionization, and all that material combining together, which are the reactants actually forming the products, which are, the larger chemicals and molecules. At the other extreme, some reactions reach equilibrium immediately, with very little product being formed. These two examples are representative of very large K values and very small K values, respectively. They are essentially two driving forces that control the extent of a reaction and determine when equilibrium will be established. Meaning, if you have stars as large non-equilibrium dissipative events, they are wanting to achieve equilibrium, but the only way they can do that is by driving themselves to the lowest heat content, which is enthalpy, and driving themselves to the greatest amount of randomness or disorder, which is called entropy. Hopefully people understand those two concepts. They were a bit difficult when I took my first physics classes and chemistry classes. Reactions with negative change in H values, enthalpy or heat content, are exothermic, and reactions with positive change in S values, entropy or randomness, proceed to greater randomness. The second law of thermodynamics states that the entropy of the universe increases for any spontaneous process. And for the most part, stellar evolution is spontaneous. This means that the entropy of the system may increase or decrease, but that if it decreases, then the entropy of the surroundings must increase to a greater extent so that the overall change in the universe is positive. In other words, change in the universe equals the change in the system plus the change in surroundings. What that means is that if you have a star cooling and becoming more disorganized in its interior as the elements combine together making molecules, that is always going to go up in entropy because it cannot get the entropy to increase in the vacuum, because there's very little material in the vacuum. The majority of the material is inside the star itself. If it was the vacuum that increased the entropy, then the star, well, it wouldn't go up in disorder. It would always remain the same. But clearly that doesn't happen. Stars cool, they shrink, they die, and they differentiate their interiors, becoming what scientists call planet. But there's just a few thoughts for you, of course. It also goes over change in free energy of a system, the Gibbs equation on the bottom as well. Here's some examples for aqueous solutions, solids, and gases when they combine together. I'm going to go ahead and review that. But there's just so much more to it. And if we just look at stellar evolution as being something of a chemical construct, electrochemical construct, then we'll have a much greater grasp on nature than what has been provided to us via 1950s fusion star models, which do not refer to reality. On another side note, the search for these neutrinos and building these very advanced neutrino detectors and various other constructs, I think those benefit contractors more than actual scientific insight. I think the reason why they build them is because it all started from a groupthink orientation to, well, the sun is a fusion reactor and it has neutrinos coming out of it. But then they failed to find the neutrinos, and then they invented neutrino oscillation, and obviously some prizes were handed out for the discovery of this neutrino oscillation when they didn't discover anything at all. They just had to keep up the appearances that they actually know what they're talking about. But clearly they don't, because stars are electrochemical in nature, not nuclear, not thermonuclear. Thermochemical, not thermonuclear. The events that happen in stars can be singly, doubly, or triply ionized, being that the elements have their electrons ripped away in very, very, very large amounts. So you could have iron having most of its electrons ripped away, but that's as far as it goes. There's just higher and higher levels of ionization. The events that take place inside of stars are not nuclear whatsoever. It's quite disappointing that they've made it such, but as with academia, that's how things go sometimes. All right, everybody, have a good day, and hopefully everybody had a good Thanksgiving, and I'm looking forward to the next few days. All right, later.